Okay, in the preceding video, which many of you will have ignored, either because you haven't had differential equations or because you think you already know it, or because you just don't want to think about it, explain the solution to a differential equation that results from two different situations. They both are covered by this situation, by this equation. And the solution to this equation, if you have this setup where the capacitor is initially uncharged, and you have a switch in here, and you throw the switch and the source starts charging the capacitor through the resistor. The solution to that equation is going to be this. The charge as a function of t is equal to the capacitor times the voltage of the source times 1 minus e to the negative t over RC. Now, I'm not going to explain to you. I've already explained where that comes from. It's not that difficult to understand. But let's see what that tells us. Let's see how the system behaves and see if that's consistent with the way the systems behave in lab and in our general experience. First of all, this 1 minus e to the negative t over RC is an expression that you should, if you've had a good pre-calculus course, understand based on pre-calculus. And then if you've had a good calculus course, you'll have even a deeper insight into the meaning or into the nature and the way this expression changes with time. But what you should understand is that this is e to negative t over RC. Now, e to the negative t over RC is what? 1 over e to the t over RC. As t gets large, e to the t over RC gets large, so that 1 over e to the t over RC approaches 0. So, as t gets large, e to the negative t over RC approaches 0. Not because your calculator tells you so, but because your laws of exponents and your common sense tell you so. Okay, so the negative t, e to the negative t over RC approaches 0, so that 1 minus e to the negative t over RC is going to approach 1, which means that your charge will approach capacitance times source voltage. Now that's exactly what we would expect. We'll see why in a minute if you don't already see it. Also, when t is 0, what do you get? When t is 0, you get e to the 0, which is 1, and here you get 1 minus 1, which is 0. Your charge when t equals 0 is 0, and your charge exponentially approaches, or asymptotically, exponentially and asymptotically, approaches C times source voltage. Now, what's the meaning of C times source voltage? Well, assuming we understand that capacitance is charge per volt, okay? It's the ratio of charge held on the capacitor to the potential difference. That's exactly what we would get. If we solve for C, we get Q over V sub S, right? Okay, if we set C V sub S equal to Q of T, we get C equals Q of T over Vs. In the long run, the charge on the capacitor will become great enough that the capacitor has a voltage equal and opposite to that of the source. When the magnitude of the charge on the capacitor is equal to the voltage of the source, then the charge on the capacitor is going to be C times the voltage of the source. So this is exactly what we expect. So, for an initially uncharged capacitor, this makes a lot of sense. And it makes even more sense if you understand exponential functions. Okay? You understand that the rate at which charge will flow here is equal to the difference between the source voltage and the capacitor voltage. So that the rate of charge flow will, being proportional to the difference, will exponentially approach the source voltage. And I actually need to write things out to make that clear. You need to understand the exponential function as what arises when a rate of change is proportional to a given quantity. Okay, and I could say that more clearly, but you want to think about the meaning of an exponential function. Again, I'm finding I need to write things out to say anything really clear about that. So if that wasn't real clear, my apologies. Okay, and we have another situation here. That's this situation. If we have a switch here and throw it so that the charge is initially 0, this is what's going to happen. This is how the charge is going to build. And of course we know that this graph, I hope we know that this graph does this sort of thing. You have the full charge on the capacitor, and the charge exponentially approaches that in a way that we make very clear in a later lab. Okay. In this case, we have a switch here that can go here or here. So we can complete the circuit here, in which case the source is interacting with the capacitor, or we can throw it over here, in which case the source is out of the picture and the capacitor and the resistor interact. Okay. In that case, we say, okay, let's just charge up the capacitor. Okay, so we just close this switch, go away for a while, come back. The capacitor is completely charged, and of course that charge will be what? It'll be the product of the capacitance and the capacitance and the voltage of the source. So, but you're going to have some charge on the capacitor. And then you're going to throw the switch over here at the t equals 0 instant, at the time you choose to start your clock, so that the charge on the capacitor will build. Now, initially there's no charge on the capacitor, charge on the capacitor when you throw the switch will decrease. Okay, the capacitor will discharge through the resistor, because when you have the switch over here, no current can flow through the source. So what if this is, if charge drifts through the current, to say it more properly, in such a way that it decreases the charge on the capacitor, that means you're effectively transferring charge from one plate to the other until the capacitor is discharged, until there's no charge left. As long as there's charge on the capacitor, it will continue to flow through the resistor. So you initially have a charged capacitor, and it's going to discharge rather quickly at the beginning. Okay, but as it discharges, the voltage on the capacitor decreases, which means the voltage across the resistor decreases, which means that the current decreases, and the current is the rate of change of the charge. And I just saw something on the camera that disturbs me, so I'm going to come back to that. I don't know what I just saw.